Okay, so good evening, everyone, and I welcome you all to today's live session. Okay, so I welcome you all to today's live session for the course Elements of Mechanical Vibration, NOC25-ae17. We are into the week 8 live session for this course, and we have already completed 7 live sessions up till now. So, this week was mostly concerned about again the 2 degree of freedom system, but this time it was more focused about vibration absorbers and tuned mass dampers. So the basic concept that we discussed last week was that how do we deal with a 2 degree of freedom system, or basically multiple degree of freedom system. So we learned about how should we derive the equation of motion, how should we deal with the modes and mode shapes, and what is going to be the general solution of the system, which will be the amalgamation of the two modes of the system. Anyways, this week it is mostly concerned about how the 2 degree of freedom system essentially works as vibration absorbers and tuned mass dampers, depending upon how do we apply or use the second mass and the second stiffness. Okay, so I hope that you people have already gone through the 3 lectures for this week. And so we'll be starting with the first question. Just a second. Okay. See, last time when we discussed about the 2 degree of freedom system, both the masses were constrained, right? Now this time the masses are not constrained. They are not constrained. There is no horizontal constraint on the mass. It can go up till infinity. So earlier when we had, like, my system was somewhat like this, we had two boundaries like this, and then there were springs. So in this case, there is a limited amplitude which mass m1 or mass m2 can counter. It can go further and backward. There's a limited amount. But in this case, what is happening? The amount is, it can be infinite. It may happen that the mass m1 or m2. Can you please switch off your mic? Thank you. So in this case, the mass m1 or mass m2 can have infinite amplitudes as well. So the question says that we need to find out the free vibration solution of the unrestrained system. Unrestrained because it is not restricted in the horizontal direction to have only a certain amount of amplitude or a certain amount of displacement. Of the system shown in the figure below, the parameter values they have given us and the initial condition is also given. Okay. So for this system, what do we have? It is actually easier to solve this system rather than the previous system because there is only one spring that is contributing over here. So we have two masses. Again, these two masses are going to have two independent movements, x1 and x2. So it is a 2 degree of freedom system and we require two equations in order to find out the response of the system. So for mass m1, we have the movement x1 of t. Now because of this, inertia force is going to act m1 x1 double dot, and then force due to the spring is going to act, which is going to be k x1 minus x2, x1 minus x2, because the spring force is going to be dependent upon the relative displacement between the mass m1 and m2, not the absolute displacement. Okay. Similarly, for mass m2, we have x2 of t, inertia force m2 x2 double dot, and then spring force, which is going to be m2 x2 minus x1. So the equation of motion is going to be, now you see over here there's no forcing, right? There is no external forcing. So m1 x1 double dot plus k x1 minus x2 is equal to 0, m2 x2 double dot plus k x2 minus x1 will be equal to 0. Now what do we do after that? See, we need to find the solution. Last time also I discussed that using the example of a coordinate system, that when I have x and y, which are two separate independent coordinates, and if I want to write the vector p such that it is at a distance x naught over here and y naught over here, I write p vector as x naught I cap plus y naught j cap, where I cap and j cap are unit vectors in the respective direction, and these two unit vectors are independent of each other. So we use the concept that if I have a planar system which has two coordinates, and if I want to write any point on that planar area, so what I can do is I can use I cap and j cap, which are two independent unit vectors. So what do? We use the linear combination of these two independent vectors to write any position vector for any point P on the xy coordinate. Correct? So what do we require? We require at least two independent unit vectors. Similarly, for a 2 degree of freedom system, if I get any two independent solutions, then I can get the total answer or the general solution of my system as a linear combination of both the independent solutions. And then both the independent solutions were what? They were the modes, right? Because if you remember that for the 2 degree of freedom system, there were two modes, and during those two modes, the system was what? Vibrating in that particular mode only. There was no contribution of the second mode. Right? So like if I have two frequencies, omega 1 and omega 2, which are the two modal frequencies. So if I oscillate or give the initial condition to my system corresponding to omega 1, both my masses are going to oscillate with the frequency omega 1. There is no contribution of the omega 2 mode. Similarly, if I give the initial condition corresponding to the omega 2 mode, there is no contribution of the omega 1 mode. So these two the solutions corresponding to the two modes, right? The solutions corresponding to the two modes are essentially the two independent solutions that we are looking for. If I get these two independent solutions, I can write any general solution of my system using the linear combination of these two. Okay, I hope this concept is clear. So again, if we need to find out the general solution, we need to find out the two independent solution, and those two independent solution we are going to get from the modal frequencies. So in order to find out the modal frequencies, what were we doing? We were assuming x1 as x1 cos of omega t plus phi 1 and x2 as x2 cos of omega t plus phi 2. Okay. Then if I use these and put it in the main equation, these two equations, I guess there is some lag between what I'm writing and what is getting displayed. That's fine now. Okay, so if I put these two solutions that I've assumed in the main equation, what is going to happen? I'm going to get a equation something like this: minus m1 omega square plus k x1 minus k x2 is equals to 0, and minus k x1 plus minus m2 omega square plus k x2 is equals to 0. Again, I can write it in matrix form, and then in the matrix form, since x1 and x2 cannot be 0, so what do? I make the determinant equal to 0, which will give me This is equal to 0. So now when I find the determinant, not minus, it should be plus m1 m2 omega to the power 4 omega to the power 4 minus, if I'll multiply this and this, so basically we are going to get minus of m1 plus m2 k omega square, and then k square minus k square is going to be 0. See, this is the reason that I chose this problem, in order to give you understanding of what is happening in this system. So over here, I take omega square common, m1 m2 omega square minus m1 plus m2 is equal to 0. Now omega square cannot be equal to 0. So definitely omega square is going to be m1 plus m2 divided by m1 m2. Okay, there should be a k. Yeah. So omega is going to be nothing but okay. This is the case when we consider omega not equal to 0. What if omega is equal to 0? Omega is equal to 0. What does this actually mean? Just a second. Okay, so what does this actually mean that omega is equal to 0? So this particular case actually means that the frequency of oscillation is 0, which means there is no oscillation that is happening between M1 and M2. Okay, there is no oscillation that is actually happening between M1 and M2. Now, when is that going to happen? When is that going to happen? So, suppose if I have this mass M1, there is a spring, and then I have a mass M2. If I give it a displacement of x naught and this a displacement of x naught, what is going to happen? Both mass m1 and m2 are going to get displaced by x naught, and there is no stretching or no compression of the spring. There's no oscillation. I'll pick up the mass, put it like this. Nothing is happening to the system, which means that the frequency is 0, which means that my system is behaving like a rigid body. The system is behaving like a rigid body, right? And when you will find the eigenvector or the vector along this modal frequency, you are going to get it as x1, x2 at the first mode as 1, 1. Which means if both of them are given the same amount of displacement, it is going to behave like a rigid body, which means that omega is going to be equal to 0. So this basically shows a rigid body motion. This was not the case when we were considering a restricted system, right? There, the first mode was actually having a mode shape as 1, 1, right? But still there was a frequency present because there were oscillations because of the restriction from both the sides. Here, because of the unrestricted case, the first natural frequency is nothing but 0, which means the system is going to behave like a rigid body. Now coming on to the second case, which is this one. In this case, what is going to happen is that one displacement and the other displacement are going to be in the different direction, definitely. Or even if if you displace m1 or m2 in the same direction but by different amount, then the oscillation is going to happen. Anyways, we are mostly concerned about the eigen solutions or the modal solutions, right? So for this, the modal shapes are found to be x1, x2 at the second mode 1 and minus 0.5. Okay, I hope this is clear. Now we have the initial condition which is given in the question, right? Initial condition is given in the question. We need to find out the free vibration solution. Free vibration solution. So we have x1 at 0 as 0. Sorry, not 0, it is 0.1. Other than that, everything is 0. Okay, so what do? We'll just, now we have the solution. We have the modal solution, right? We have the modal solutions. So we just need to find out the linear combination of the modal solutions in order to get the solution of the free vibration. So we write the general solution x bar of t as c1 1 1 cos of omega t. Now for the first case omega is 0, so it is just going to be phi 1 plus c2 1 minus 0.5 cos of 17.32052 t plus phi 2. Anyways, this value is going to come out from here because we have the value of m1 and m2. We have m1 and m2 as 1 and 2 kgs and k as 200. So from here omega 2 is going to be under root of 3 into 200 divided by 2. It's going to be under root of 300 and come out as 17.3205 radians per second. So this is going to be the general solution. Now, as you can see, we have the modal solutions. What we have done is we have just written the linear combination using the constant C1 and C2, and that is what we need to find out. We need to find out the values of C1, C2, phi 1 and phi 2. Correct? So now, since we have four initial conditions that has been given, which are x1, x2, x1 dot and x2 dot. We have four initial conditions and four variables. Okay, so we have a unique system and then we can find out the values. Okay, so from here we can write x1 of t as the above part of the vector, which is c1 cos of phi 1 plus c2 cos of 17.3205 t plus phi 2, and x2 of t as c1 cos of phi 1 minus 0.5 c2 cos of 17.3205 t plus phi 2. Okay, so the first initial condition is x1 of 0, which is 0.1, is going to be equal to c1 cos of phi 1 plus c2 cos of phi 2. Second, x2 of 0, which is 0, is going to be c1 cos of phi 1 minus 0.5 c2 cos of phi 2. Other than this, we have two velocities which are going to come out by differentiating x1 and x2 with respect to time. So the first terms, which is c1 cos phi 1, will go to 0 since it's a constant value. So only second term will play the role. So x1 dot at 0, which is 0, is going to be what? Minus, not minus, yeah, minus, because cos is minus sign, 17.3205 3205 C2 sine of phi, and x2 dot of 0 is going to be 0, which is minus 8.66025 C2 sine of phi 2. So C2 into sine of phi 2 is essentially 0, which means that phi 2 is either 0 or either pi. Because C2 cannot be equal to 0. See, our general solution should have contribution of C1 and C2 both. If we consider C2 as 0, it means that the second mode does not have any solutions. Only the first mode is having the solution, which is when the system behaves like a rigid body, which is not possible, since I already told you if only the displacement and direction of x1 and m1 and m2 are same, then only the system is going to behave like a rigid body. Other than that, it is definitely going to have vibration. So C2 cannot be equal to 0, which means either phi 2 is equals to 0 or pi. Okay. Now, other than this, if I use the first two equations, then I'll get the value as of C2 as plus minus 0.0666, and we'll have C1 cos of phi 1 as 0.0333. Now we do not need to find out the separate value of C1 or cos phi 1, because C1 cos phi 1 appears together only. So we can just use it like that. So finally, using all these things, we get the final solution as x1 of t as 0.0333 plus minus 0.666 cos of 17.3205 t plus phi 2. Now phi 2 you can take 0 anyways, or pi, and x2 of t as 0.0333 plus minus 0. Okay, here it should be a 0.0333 cos of 17.3205 t. So this is going to be the general solution of the system. What is interesting over here is that for an unrestrained system, the first modal frequency is 0, which gives a constant value as a solution, which is same again. Why? Because the system is behaving like a rigid body. Only the second mode is responsible because of the system, is the reason that the system can vibrate. The first mode is never going to let the system vibrate. I hope this is clear. Now we'll come on to the second question. So I took up this question because I find it interesting. See, there's a rigid rod of negligible mass. Okay. Then it is having a length of 2L, pivoted at the middle of point, and is constrained to move only in the vertical plane by the spring and the mass. So it is basically constrained over here. Now we have to find the natural frequencies and mode shapes of the system. So the first question that comes to our mind is that how many degrees of freedom are we talking about over here? I mean, we learnt initially that the number of masses is going to give us the number of degrees of freedom. Over here, we have three masses, 2m, 2m, and m, right? We have 2m, 2m, and m. Number of masses are what? 3. So the first thing that comes to the mind is that there are three masses. So we need to find out three equations and the three modal frequencies and mode shapes, right? But what is interesting over here is that the two masses 2m and 2m are actually connected to each other by a rigid rod, which is specifically mentioned over here. A rigid rod. If it would have been an extensible rod or extensible material, we would have had 3 degrees of freedom, right? But here we have a rigid rod, which means that no matter what is the displacement, Definitely theta is going to be small only, but this 2m and 2m are always going to have the same amount of displacement. Only the direction is going to be different, right? So if the system is initially like this and then it goes to like this value and this value x naught, not x naught, maybe we should call it y and y. It is always going to be the same, only the direction of movement is going to be different. So now this system becomes what? It becomes a 2 degree of freedom system because we are concerned about only two independent motions. One is of angle theta and the other is of the mass m, which is in this direction x. These are the only two. These are the only two displacement that we are concerned about in order to finding out the uh, equation of motion and then finding out the frequencies and mode shapes. Okay, so when we look over here for the mass m, and then we have a spring k. Okay, and this is the displacement x. Now, if m is going in the downward direction, what are the forces that are acting on it? Firstly, then inertia force is acting in the above direction as mx double dot. Then, because of the spring, we'll have another force which will be in the above direction as kx. Okay. Apart from that, there is another spring above this spring. Now, this spring, which is connected to 2m. Okay. Now, this 2m is also getting displaced. Something like this, which is y. Okay. So, if this is going up with y, so definitely the spring force that will act on this mass m will depend upon the relative displacement between 2m and m. So if m is going downward with x and 2m is going upward with the displacement y, so then the total displacement of the spring k is going to be nothing but x plus y, right? So a spring force will also act in the above direction. I'll write it as plus k into x plus y. We considered y in the above direction, that is why it is a plus over here. If it is in the downward direction, it is going to be x minus y. So this is going to be x plus y. Now for this mass, we can write the equation of motion as mx double dot plus kx plus kx plus y is equal to 0. Okay, is equal to 0. This is going to be the equation. Now, apart from that, using the this displacement of rod and relating it to theta, because see, we are looking at x of t and y of t, which is considered y as a function of time over here. But then y is dependent upon theta as L to theta of t, L into theta of t. So we can replace y of t as L into theta of t. Okay. So finally, the equation of motion becomes mx double dot plus 2kx plus kl theta is equal to 0. This is the first equation of motion. Okay. Now coming on to the masses that are attached on the rigid rod. So the rigid rod does not have its own mass, so it is not going to have any kind of contribution. But there are two masses that are there present on the end of the rods, each of mass 2m. So the total inertia because of these two masses is going to be what? Firstly, a mass suspended at a distance of L from the point of pivot point, it is going to be ml square. Here we have 2m, so 2ml square into twice, because we have two masses both go in the same sink, right? Both are observing, like both are getting the inertia force in the same direction. See, this mass is going upward, this mass is going downward. So it is going to observe a inertia force in which direction? Clockwise, and this is also going to have it in the clockwise direction. So we can uh, add up the contribution of inertia. So we are going to have 4ml square theta double dot, which is the inertia force. Other than that, what are the forces acting? We have two springs, one spring over here, another spring over here, which is then connected to the mass. For this spring, we know we have to use the relative displacement, correct? Which is going to be what? The relative displacement, which is going to be what? L theta plus x into k. Since this is getting displaced in the upward direction, the spring is going to pull it in the downward direction. So again, the moment is going to be in the clockwise direction. For this mass, what do we have? The displacement is k, or the force is k, r, not r actually, it's L, theta, k into L theta. Now this mass is coming in the downward direction. So again, the spring is pushing it upwards, like pulling it upwards. Again, the moment is what? In the clockwise direction. So everything will get added up. Everything will get added up. So we are going to have plus k L theta plus x into L plus k L theta into L, going to be equal to 0. So the final equation becomes 4ml square theta double dot plus 2k L square theta plus k L into x is equal to 0. Okay, I hope this is clear. 4ml square theta double dot plus 2k L square kl, yeah, x is equal to 0. So this is the second equation of motion. So now if we assume the solution x as x cos omega t plus phi and theta as theta cos omega t plus phi, and then again put it in the two main equations, what do we get? We get the equation in the matrix form as 4ml square omega square plus 2kl square kl kl minus m omega square plus 2k into theta, this theta, and x is equals to 0, 0. Again, capital theta and capital X can never be equal to 0. So the only way that it is going to be equal to 0 is that we put the determinant of the first matrix equal to 0, which is going to give us 4ml square omega square plus 2kl square minus m omega square plus 2k minus k square l square is equal to 0. So if we'll break it, what are we going to get? We'll have 4 m square L square omega to the power 4, and then we are going to have minus 8 m L square k omega square minus 2 m k L square omega square plus 4 k square L square minus k square L square is equal to 0. This is going to give us 4 m square L square omega to the power 4 minus 10 m k L square omega square plus 3 k square L square is equal to 0. We can take L square common and remove it. So finally we are going to get 4 m square omega to the power 4 minus 10 m k omega square plus 3 k square is equal to 0. We can use the concept that we use to find out the roots of a quadratic equation in order to find out the values of omega square, and then from omega square we can do the under root and take the positive values as the values of frequency or the modal frequencies. So essentially omega square is going to be k by m into 5 by 4 plus minus under root of 13 by 4. So this is going to give us 0.3486 k by m and 2.1514 k by m. So the two frequencies are going to be omega 1 as 0.5904 under root of k by m and omega 2 as 1.466 under root of k by m. These are what? These are the frequencies that we were supposed to find out in the question, right? So in the question, we were supposed to find out the natural frequencies, which were what we have computed over here, and the mode shapes. So again, the way of finding out the mode shapes is R1, which is x of 1 by theta of 1 minus 4 m L square omega 1 square plus 2k L square divided by minus of kl. Okay, so this will turn out to be, what do we have to do anyways? We know the value of omega 1, we put the value of omega 1 in this. Okay, everything will get cancelled out, only one L will remain, and so it will come out to be minus 0.6056 L. So corresponding to this, the mode shape is going to be what? Mode shape, which is x of 1, which is this and this for the first case, 1 6056 L theta of 1. For the second mode shape, R2 is x of 2 by theta of 2. So this is again going to be 4m L square. Instead of omega 1 square, there is going to be omega 2 square plus 2k L square divided by minus of kl. This will turn out to be 6.6056 L. So x2 bar at 2, which is the first mode shape. This is the second mode shape. It will turn out to be 6056 L for the second theta. Okay, I hope this is clear. So we were supposed to find out the mode shapes for a 2 degree of freedom system like this, which has 3 masses, but it is essentially a 2 degree of freedom system. The reason being that the first 2 masses are connected by a rigid rod, right? coming on question number 3, which is now about a vibration absorber. So, the concept of vibration absorber actually comes because of the problems that we face in the day-to-day life, right? So, for example, there's a machine which is working at a high frequency, and or let us like high frequency is not mandatory at a frequency near to its maybe resonant condition or something like that. So, what is going to happen? It is going to show vibrations, right? Now, because of that vibration, the floor is going to suffer with vibration, right? The person who is standing, if the floor is not damped properly, he or she is going to feel the vibration that is happening in the system, right? So, in that case, it is very important that we actually work on vibration absorbers. Like, for example, if we take the concept of what we have in our home, I think everyone has seen how a semi-automatic washing machine works, like which has two separate buckets. One is for washing of the clothes, and second is for the drying of the clothes. So usually, what happens is that if the mass in the drying drum, if the mass is not balanced properly, it is going to have very large amplitude of vibration, right? It is going to make a loud sound, and then it is going to show large amplitudes, right? Now, why is that? That is because of the vibrations. Even if it is not having a very large amplitude, still it is going to have vibration. You can hear those vibration when that drying drum is working. So you must have seen that those kind of washing machines, they have four rubber supports at their bottom, and through that rubber support it is kept on the floor. Now those rubber supports, what are they doing? They're absorbing the vibration. They're not letting the vibration get transferred to the floor, right? So that is how the work of vibration absorber, it is very important. And then we have its use in every or most of the things that we do daily. Like for example, we have this laptop. Everyone has a laptop. If you'll see, it has rubber supports in the bottom. Yes, it is to prevent scratch, but then it is also important for us to keep the laptop isolated from any kind of a surrounding vibration, because it can cause harm to the system. Okay. So now this question is about vibration absorber. Okay. So before going into the question, I'll write some equations. So firstly, for a vibration absorber, I have a mass, which is the parent mass, which is the mass of the machine that I'm working on. Then it is connected to the floor through a spring. That is how we model a single degree of freedom, a system to in terms of a single degree of freedom system, right? We model it in terms of a spring mass system, like this. So it is having a vibration of F naught sine of omega t. I don't want it to vibrate. Okay, wherever this vibration is coming from, I want my mass m1 to be static with respect to time. Okay, I want it to be static with respect to time. So what will I do? I will suspend a mass m2. Let us say it is k1 by 2. It is k1 by 2. A mass m2 with a spring stiffness k2 from mass m1. From mass m1. Okay. Now this suspended mass is going to help me with absorbing the vibration. Now it may seem a bit problematic firstly, because of our intuitive understanding that okay, if a system is vibrating and we attach one more mass through a spring, so how it is going to stop my mass from oscillating? That is what is interesting about a vibration absorber, especially the undamped vibration absorber, because here we don't have any kind of a damping. Still the vibration of m1 is getting stopped, right? So for this kind of a system, what do we have? If we write the equation of motion, how is it happening? See, this is oscillating with x1, and this is going to have a movement of x2. So for m1, we have m1 x1 double dot plus k1 x1 plus k2 x1 minus x2 is equals to not 0 but f naught sine of omega t. For this we have m2 x2 double dot plus k2 x2 minus x1 is equals to 0. Now the first thing is to again find the frequencies. So for frequency we know how do we do it. We assume the solution x1 is x1 sine of omega t and x2 as sine of omega t. Then from using this we can find out. Anyways, what we are doing is essentially we are designing M2 and K2. Up till now I don't know what is M2 and K2. But what I do know is I know M1, I know F naught, I know omega, I know K1. Depending upon what amplitude of oscillation M1 is having, we need to calculate the value of M2 and K2 in order to get zero vibration of M1. Right? So I'll define some terms, which is omega 1, which is the frequency of my parent system. Then we have delta static, which is nothing but F naught by K1. And then omega 2, which is the frequency of the absorber. So using all this, it has been already done in the book and lecture also, but I'll just write the final equation. Okay, the final equation gives us x1 by delta static is going to be equal to, okay, wait, I should write it in the next slide for, yeah. So x1 by delta static is equal to 1 minus omega by omega n square divided by 1 plus k2 by k1 minus omega by omega 1 का square 1 minus omega by omega 2 square minus k2 by k1. Similarly, x2 by delta static also we have as 1 divided by 1 plus k2 by k1 minus omega by omega 1 square 1 minus omega by omega 2 square minus k2 by k1. So this is the equation of x1 and x2, capital X1 and capital X2, which is basically the amplitude of oscillation. Now our aim is what? Our aim is to make x1 is equal to 0. That is possible when omega is equal to, here it's not omega n but omega 2. This is possible when omega is equal to omega 2. Correct? This is possible when omega is equal to omega 2. Correct? Now, if my system is actually oscillating near to the resonance condition, or I should say that it is near to omega 1, right? Then only it is going to have the maximum of oscillation. See, in the practical condition, my mass m1 can have any amplitude of vibration. Correct? It can range from any value 0 to A, where A is the maximum amplitude. So whenever I am designing a damper, vibration absorber, not damper, whenever I am designing a vibration absorber, what is going to be my aim? What is going to be my objective? My objective is going to be to make A is equal to 0. If A is equal to 0, then every other value is also going to be equal to 0. Correct? That is how it is. If it is going to damp out, if it is going to absorb the vibration at the resonance condition or at the maximum amplitude, if it is going to damp it out, then in that case, that is how I am going to design my vibration absorber. So for my system to oscillate at the natural frequency omega 1, omega should be equal to omega 1 and hence my omega 2 should also be equal to omega. This is the condition that we have. Correct? This is the condition that we have. Now, if I use this, omega is equal to omega 1, it is equal to omega 2. What do we get? What do we get when we put it in the second equation where we are calculating x2? We are going to get the equation of x2 as minus of k1 by k2 into delta static. See, over here, I have omega by omega 1 as 1. This is 1, 1 minus 1, 0. Multiplied by 0 is nothing. So I'm going to have over here only minus of k1 by k2 multiplied with delta static is going to give me x2. So x2 is going to be nothing but minus of k1 by k2 into delta static. Okay. So what can I do about delta static? Delta static is nothing but f naught by k1. So if I replace it with f naught by k1, I'm going to get it as minus of f naught by k2, right? Minus of f naught by k2. So k2 into x2 is minus of f naught. Anyways, k2, what I can write k2 as? See, we have omega as omega 2, which is nothing but under root of m2 by k2. So from here, I can write k2 as k2 as okay, I've written it wrong, right? k2 by m2, it should be like this. So I can write k2 as nothing but m2 square omega square, not m2 square, m2 into omega square. Here I can replace this as m2 omega square x2, m2 omega square x2. First thing that is to be kept in mind is that x2 is having a direction opposite to f naught. X2 is going to have a direction opposite to f naught, right? And this, okay, and then this m2 and k2 will actually be dependent upon capital X2. See, we cannot assume that this mass m2 can oscillate infinite with an infinite amplitude. If you look over here in the diagram, this we have a limit of this distance, right? This distance has a limit. I cannot say that m2 can have any amplitude of oscillation. So this limit is going to decide what are the permissible m2 and k2 by me. If I don't have this limit, if I don't consider this limit, I can simply put omega is equals to under root k2 by m, and then I can simply decide what is going to be k2 and m2, right? We can have infinite many combinations of k2 and m2. But in practical condition, we always have a limit. Either we have a limit of how much m1 can oscillate, or we have a limit of how much mass extra we can put into the main system, right? There is always going to be a limit. Now, we cannot, for a 100 kg mass, we cannot put 50 kgs extra because it is going to reduce the efficiency of the system. It is going to make my system very heavy, right? So there is always a limit either of the mass or either of how much the mass can oscillate. So depending upon the of, sorry, limit of x2. So our the design of k2 and m2 depends on the maximum allowable value of x2. Okay, we cannot just assume that okay, any m2 or k2 which is satisfying the condition omega is equals to omega 2 is going to work for us. We need to consider the limitations which are present in my system because of the design of my system. Now, coming on to the question. See, in the question we have a diesel engine weighing 3000 Newton is supported on a pedestal mount. Okay, there's a pedestal mount on which the weight is suspended. It has been observed that the engine induces vibration into the surrounding area through its pedestal mount at an operating speed of 6000 rotations per meter. So at an operating speed of 6000 rotations per meter, even through the pedestal mount, the engine is transferring the vibration to the surrounding. We need to determine the parameter of the vibration absorber that will reduce the vibration when mounted on the pedestal. The magnitude of the exciting force is 250 Newton and the amplitude of motion of the auxiliary mass is to be limited to 2 mm. This is why I gave this all understanding of the concepts I discussed over here. Because in this question we have the limitation of the amplitude of the motion of the auxiliary mass. So we have weight W as 3000, omega as 2 pi 6000 divided by 60. 6000 divided by 60 is what? Frequency. And frequency to 2 pi is going to give us omega. So this will come out to be 100 and 2 pi is 3.14 into 2. So something like 628. I'll see. Yeah, 628.32 radians per second. Okay. Then we have F naught as 250 Newton and X2 limit as 2 mm. Okay. So what do we have to find over here? We have to find out the parameters of the vibration absorber, which is M2. We have to find out, and K2 we have to find out. Okay. Now look over here. We have this equation M2 omega square x2 is equals to minus of F naught. Omega we know 628.32 radians per second. F naught we know it is 250. We need to find out the value of M2. Now over here we discussed that this x2 is going to help us decide the value of M2. We know that by definition of the vibration absorber, under root of K2 by M2, which is omega 2, should be equal to omega. We have two variables over here. Even if we find out one of them, we can find the second one. Now, if you look at this equation, we can use this equation using the maximum permissible value of x2 in order to find out the value of m2. And once we find out the value of m2, we can use equating under root of k2 by m2 is equal to omega to find out the value of k2, right? So equating this. Now, x2, this minus F naught is basically used in order to relate the direction in which x2 is going to happen. But what we are concerned about, we need to find out the value of m2 depending upon the maximum permissible value of x2. So what we can take is we can take the modulus. So we can write m2 into 628.32 square into x2, which is 2 mm. Yeah, is equal to 250. Is equal to what? 250. So by solving this, we are going to get the value of m2 as I've already calculated it. It will come out to be 0.31665 kg. So this is the first parameter for the vibration absorber, which is the mass of the suspended mass of the auxiliary system, which is 0.31665 kg. Second is we need to find out the value of K2, which is going to be omega square into M2, which is 628.32 square into 0.31665. So K2 will turn out to be 5009 Newton per meter. Now you can look over here that the mass is very small as compared to the stiffness of the spring. We need a very high stiffness spring in order to reduce the vibration of the mass M1. Okay, now coming on to question number 4. This is a bit lengthy question, but I'll try to explain it. In case you have any doubt, you can ask me in between also. So we have a motor generator set as shown in figure, designed to operate in the speed range of 2000 to 4000 RPM. We have a speed range that has already been given, permissible speed range, which is 2000 to 4000 RPM. I'll write it first. 2000 to 4000 RPM. This is the permissible speed range that we have. However, the set is found to vibrate violently at a speed of 3000 RPM due to a slight unbalance in the rotor. So it is showing violent vibration, which means that 3000 RPM is nothing but the natural frequency of the motor generator system. So we can write omega 1 as omega n because currently it is a single degree of freedom system. It is equal to 3000 RPM, which is converted into 2 pi 3000 divided by 60, 50, so 100 pi, which is 314 point, okay, 314.16 radians per second. Radians per second. This is omega 1. Next, it is proposed to attach a cantilever beam mounted lumped mass absorber system to eliminate the problem. This one. Lumped mass, lumped mass means that this is going to have a larger mass or very significant mass as compared to the rod. So the mass of the rod can be neglected. So it is going to be a lumped mass case. Okay, to eliminate the problem. When a cantilever carrying a trial mass of 2 kg tuned to 3000 RPM is attached to the set, the resulting natural frequencies of the system are found to be 2500 RPM and 3500 RPM. Okay, so the first trial where we have M2 as 2 kg. Okay, and it is tuned to 3000 RPM. K2 we don't know as of now, but it is tuned such that 3000 RPM results in 2 peaks. So basically, what's happening is that uh, so this is frequency, and this was omega 1. This was initially before the, so this blue color is for system without absorber, and this omega 1 is equal to 3000 RPM. Now a new absorber is attached to the system, and for the trial run the mass is taken as 2 kg. So for the red part, trial mass 2 kg absorber. The plot is now changed to something like this. Something like this. This is, let us say, and these values are, I guess, 2500 and 3500. Yes, 2500, 3500. Omega in RPM. Okay, now design the absorber to be attached by specifying its mass sensitiveness so that the natural frequencies of the total system falls outside the operating speed range of the motor generator system. Now we already have the operating range as 2000 to 4000. After introducing a trial mass of 2 kg, what happened was that the one natural frequency got converted into two natural frequencies. Other than that, the two natural frequencies turned out to be 2500 and 3500. However, our operating range was 2000 to 4000, right? Operating range was this. This is the operating range. This is the operating range. Now the problem is that for the operating range, I have two frequencies that are actually the natural frequencies of the system, right? So if I don't keep these frequencies out of the operating range, I'm going to definitely going to suffer with violent vibrations at these two frequencies. That is how we design the safety of a system. We need to keep the either you keep the system out of the natural frequency zone, or you already have the frequency zone that is defined for the system. So you make the system in such a way such that the resonance is away from the operating zone. So in this case, we have the specification of the operating zone. So we need to find out the values of M2 and K2 such that the both the peaks fall out of the range. Okay, I hope the question is clear, right? Okay, I hope the question was clear. Now, we already have the values of capital omega 1 and capital omega 2, correct? We have the mass as 2 kg. What we do not have is the spring stiffness. Second, we also do not have the mass of my system, right? For the system, I have only the rotation's natural frequency value. I do not have the value of mass and stiffness. So if I'm designing my system, I first need to know about what is the mass of my system, so that on the basis of that, we are going to find out the value of the new mass. The first step is to find out the mass of my system other than that of the absorber. So there is this one equation, which is a very long equation. I'll write it in the next slide. So this equation says that capital omega 1 by omega 2 square, capital omega 2 by omega 2 square, both of them is equal to, we have 1 plus 1 plus m2 by m1 into omega 2 by omega 1 square. So this plus minus we have 1 plus 1 plus m2 by m1 omega 2 by omega 1 square, this whole square, minus 4 omega 2 by omega 1 square. Okay, this to the power 1 by 2 whole divided by twice of omega 2 by omega 1 square. Anyways, for this case, we have omega 2 small omega 2 is equal to omega 1, correct? Because it was written in the question that the 2 kg mass was tuned to 3000 rpm. So omega 2 is going to be equal to omega 1. In that case, this equation will turn out to be, let us say this is r1 square, this is r2 square. So we'll have r1 square, r2 square as 1 plus mu by 2 plus minus under root of 1 plus mu by 2 whole square minus 1. Okay, this is what we have. Now, for the system, we have the value of R1 and R2. Correct. We know the values of R1 and R2. Actually, we need to calculate it, but we can calculate, right? How? Because omega 1 was what? 2500 rpm. Capital omega 2 is 3500 rpm. So R1 is going to be capital omega 1 by omega 2, which is 2500 in radians per second. It you can calculate. I've written the value already, so I'll write it. It will turn out to be 261.80 divided by 314.16, which is 0.8333. Okay, and if I use this to calculate, or maybe first I will calculate R2 as well, which is capital omega 2 by omega 2, which is 3500. When you will convert into radians per second, it will turn out to be 366.52 divided by 314.16, 1.1669. Okay, so when we use this equation for, let us say, R1, what are we going to get? We are going to get R1 square is equals to 1 plus mu by 2 with a minus, because there was plus and minus. So the plus one is going to give us the higher value, minus is going to give us the lower value, minus under root of 1 plus mu by 2 square minus 1. This will give us mu as r1 to the power 4 plus 1 by r1 square minus 2 minus 2. Okay, so when I'll put the value of r1, which I've already calculated, we'll get the value of mu as 0.1345, which is nothing but m2 by m1. Since we already have the value of m2, we already have the value of m2 as nothing but 2 kg. The value of m1 is going to be 2 by 0.1345. So m1 will turn out to be 14.8699 kg. From here, what did I get? I got the mass of my system. Okay. Now, since I have the mass of my system, I can again use this equation in order to find out the value of mu such that my R1 is corresponding to the operating range. Such that my R1 is corresponding to the operating range. Now, if you remember, our operating range was 2000 to 4000 RPM. Yes. So for 2000 RPM, if we convert it into radians per second, it will come out to be 2000 by 60. Okay. The final value I'll write 209.43 radians per second. So R1 is 209.43 divided by 314.16, 0.6667. Okay. So mu will turn out to be 0.6942, which means that M2 is going to be 0.6942 into 14.8699. This will give the value of M2 as 10.3927 kg. 10.3927 kg. Okay. But the question is that, okay, this is fine that we have calculated the value of M2, which is definitely very much higher than what was there in the trial case, and it is satisfying the 2000 condition. But the operating range is not made up of only one value. We have the second value as well, which is 4000. So considering that, okay, we have calculated for 2000 limit, is it the correct approach? No, it isn't. We need to check whether this value of M2 or this value of chosen mu actually satisfies the upper bound of the operating range as well, right? It is satisfying the, anyways, I have taken 2000 as the value. It means I've taken it in a way that at 2000 I'm going to have a resonance. Okay. This was just for, like, whenever we are solving this kind of question, we are using some limiting values. But we should, if for a practical case, we should always take it less than 2000, so that even if when my system is operating at 2000, it does not encounter resonance. Okay. So now in order to check whether it is also satisfying the upper bound condition or not, we'll just check firstly R2, which is going to be equal to 1 plus mu by 2 plus under root of 1 plus mu by 2 square minus 1. So we'll put the value of mu over here and it will turn out to be 2.2497. Okay, which will give omega 2 near to something like 4499.4 RPM, which is definitely greater than 4000 RPM. So whatever the mass that we got from the first condition, it is satisfying the second as well, so it will work. So we have finalized the mass M2 as nothing but 10.3927. Okay. The second thing that is to be evaluated is the stiffness K2, and we have to do nothing but K2 as omega square M2, which is 314.16 square into 10.3927. This will turn out to be 1.0188 10 to the power 6 or mega Newton per meter. I hope the idea was clear that what were we actually doing with the system, right? So now we have designed the system in such a way such that it falls outside the operating zone. Okay, now coming on to question number 7. Sorry, not 7, this is 5. Okay, we still have two questions remaining and around half an hour of time. Okay, I'll try. So a rotor having a mass moment of inertia J1 as 15 kg meter square. So we have J1 kg meter square is mounted at the end of a steel shaft having a torsional stiffness of 0.6 meganewton meter per radian. So we have K torsional of 1 as 0.6 meganewton meter per radian. Then we have the rotor is found to vibrate violently when subjected to a harmonic torque of 300 Newton, oh sorry, 300 cos 200 T Newton meter. Okay, so torque is 300 cos 200 T Newton meter. Okay. A tuned absorber consisting of a torsional spring and a mass moment of inertia kT2 and J2 is to be attached to the first rotor to absorb the vibrations. Find the values of kT2 and J2 such that the natural frequencies of the system are away from the forcing frequency but by at least 20%. Okay, so we have kT2 and J2 as the unknowns, and kT2 and J2 should be such that omega 1 and omega 2 be at least 20% away from omega. Anyways, as it is written in the question that the rotor is found to vibrate violently when subjected to this harmonic torque, which has omega as 200. So omega is definitely going to be the natural frequency of the first system. Okay. Anyways, we have stiffness and moment of inertia given, so we can calculate also omega 1 as under root of k by m, which is 0.6 into 10 to the power 6 divided by 15. This is going to be, okay, this is going to be come out as 200. Let me check. Yeah. So basically the harmonic frequency is given at the natural frequency. Okay. But this time we need to tune it, need to attach a new mass through the stiffness such that it absorbs the vibration, right? And the natural frequencies of the new system should be at least 20% away from the natural frequency of the original system, right? It should be at least 20% away from the natural frequency of the original system, right? That is what we are supposed to find. So something like this is the current case, and we have to convert it into something like this. Something like this, right? With omega 1 and omega 2, which should be at least 20% away. Okay, at least 20% away. So for the 20% away, we should have 20% less than omega 1. Correct. So we'll have omega 1 as 1 minus 20 by 100, which is 0.8 omega 1, and omega 2 as 1 plus 20 by 100, which is 1.2 omega 1. Or omega 1 is equal to omega anyways. So this is what we are supposed to do. Anyways, again, we'll have to come to that particular equation that we were using in the previous question, which was, maybe we can just assume some parameters first, which is mu, which is j2 by j1. Then we'll have r1, which is omega 1 by omega 2, and r2 as capital omega 2 by omega 2. Okay, so r1 square comma r2 square is going to be nothing but 1 plus mu by 2 plus minus under root of 1 plus mu by 2 square minus 1 minus 1, right? So, excuse me. Firstly, what is this? It is nothing but 0.8 of omega 1, which is 0.8 of 160 radians per second. Okay, we have the value of r1 square. We need to find out the value of mu, because from mu only we are going to get the value of j2. j1 is already known to us, correct? Now, if you put it over here, 160, okay, but r1 is going to be 160 by 200, 0.8. So 0.8 square is going to be 0.8. Okay. So when you'll solve it, you'll get the value of mu as, I've already done it, you'll get the value of mu as 0.2025. Okay. So from here we can get the value of J2 as 0.2025 into 15, which is 3.0375 kg meter square. Okay. Anyways, this is going to satisfy the condition of having the minimum value, not minimum value, the small new natural frequency to be at a separation of 20% from omega 1, right? But what about the higher one? We need to be concerned about the higher one as well. So for that, we'll just check for the chosen value of omega 2. So if I try to evaluate the value of R2, 1 plus 0.2025 by 2 plus under root of 1 plus 0.2025 by 2 whole square minus 1. So R2 square, I think I've calculated it. Okay. R2 will turn out to be nearly equal to 1.25, which is anyways greater than 1.2, which satisfies the upper bound. So the mass that we selected, M2, sorry, not mass, here it is inertia, because it's a torsional system, J2 as 3.0375 kg meter square will work for us. Apart from this, we also need to find out the value of kt2, which is going to be nothing but 200 square into 3.0375, which will turn out to be 121.5 kilonewton meter per radian. Okay, I hope this is clear and there is no doubt for this question. This was just the extension of the previous question. Okay, so I took this so that it will be helpful for you to understand what we are doing for this kind of a system. Coming on to question number 6. Yeah, it's fine. So for this kind of a viscous damper, so I've taken this kind of a question because this was there with your assignment problem. Anyways, you can go into the derivation of how this is happening. You can find it in the book of W.T. Thompson over there for a modal viscous damper. So over here, if we have the mass ratio, which is mu, given to us 0.2, which is nothing but m2 by m1. I'm going to just use the formula. We have the optimum damping value formula, eta naught, as mu by under root of 2, 1 plus mu, 2 plus mu. Mu by 2 into 1 plus mu into 2 plus mu. So if we'll put the value of mu over here, we are going to have 0.2 divided by under root of 2 into 1.2 into 2.2. This after calculation is going to give a value of 0.087. Similarly, for omega optimum, we have omega by omega n given in the form of under root of 2 by 2 plus mu. This will turn out to be 2 by 2.2 under root, and it will be 0.9535. So these are the optimum values, and if you select this kind of optimum value for the tuned mass absorber, then yeah, tuned vibration absorber, then we are going to have the minimum. We are going to have the minimum amplitude. Yeah, coming on to the last question, we have this kind of a spring mass system which is attached to a disk of mass m in such a way. Now what is happening is over here is that this question is basically related to uh, the damped mass absorber. Okay, up till now, what we were discussing was about like leaving the previous question, we were discussing about vibration absorbers, which were undamped. They were not having the component of damping. But last question and this question, they are concerned about the damped mass absorber, which means that initial cases were more about we had a primary system, M1 and K1, and then there is, I'll make another just to differentiate. So in the first case, what were we doing? We were attaching another spring in mass K2, mass M2 and stiffness K2. This is what we were doing for the case of undamped vibration absorber. Over here, we are attaching a a spring. Along with that, we are also attaching a dashpot and then a mass M2. This is a damped vibration absorber. Here we are also having a component of damping. So in that case, what will we do? Okay, so this is a bit sophisticated system, a bit complicated. It's looking just complicated, otherwise it is very easy. We have already discussed a lot about how to find the equation of motion of such kind of system. So for this kind of system, what we are doing is we have attached the system in such a way over here, so that we want that the steady state oscillation of this mass is what? Zero. Okay. Though the forcing is happening on this mass only, but we want it to be equal to zero, right? So this mass is attached through a pulley to a disc of mass capital M, which is rolling without slipping on the floor. Now, if you look over here into the system, we have two masses and there is no rigid link in between it. Right? There's no rigid link. Like if mass K2 would not have been there now, this would have become a single degree of freedom problem. Why? Because the displacement of the disk R and the displacement of M was going to be same, right? But now there is a spin K2, which is going to cause some kind of a deformation in between them, and that is going to have so then this capital M and small m are going to have a relative difference between their respective displacements. Okay. So we need to find out the equation of motion, which is going to be two equations. And relating to that, we'll find out the condition which is required to find out that when the displacement of m is going to be zero. So firstly, if you look into the mass small m, this one, it is having a forcing f naught sine of omega t. Okay. So if it is getting displaced in this direction, inertia force is going to act in the upward direction. M x double dot. Spring force kx and dashpot force cx dot. Apart from that, this chord, this one, it is going to apply force P, okay, in the upward direction. For now, I don't know what is the value of P. All I know is that here it is going to be P and here also it is going to be P. Okay. See, the chord, if I'm considering this as x1 and the chord is considered as inextensible, then this point is going to have a deformation of what? X1. Correct? I hope this is clear. This point is going to have a deformation of x1, while this point, how much is it going to deform? See, the disk is rotating without slipping. Rotating without slipping. So if it has made some rotation, it has covered some distance. Let us say, oh, okay, this is the disk earlier. This is the disk now. Let us say this point was here, R. Now it rotated like this. The point will come over here, and there is this distance. Let us say which is y. For here we can consider this displacement as y. So in that case, P is going to be nothing but K2 x minus y. For now, we are considering it as y. So it has rotated by an angle theta. We know that for the case when there is a rotation without slipping, this y can be related to r and theta as r theta. Anyways, this is true only when theta is small. We are considering a small oscillation, right? Not large oscillation. Y is going to be equal to r theta. So we can replace y over there. Okay, so for the first, this case, we are going to have the equation of motion as m1 x1 double dot plus kx plus cx dot plus k2 x minus r theta is equal to f naught sine of omega t, right? I'll just cross check once. Yeah, perfect. So this is the first equation. Let us call it as 1. Okay. Now for the drum. Sorry, disk, not drum. The disk. Okay, we have a spring over here. We have a spring over here. This spring, K1. Now we assume that it is going in the forward direction and the displacement is theta. Okay. So if it went to the forward direction, rotating, its center of mass moved by an amount what? Its center of mass moved by an amount, r theta, right? Now, this K1 is going to introduce a force in the backward direction. So I can replace this with a force K1 r theta. Similarly, this spring is also going to introduce a force K2 r theta minus x because there is a relative displacement of the spring. Correct? Other than that, this system is actually rotating. So we are more concerned about the angular displacement. So if we consider the inertia as I naught, which is I plus mr square, I plus mr square. Okay, and we write the inertia moment to be equal to the moments because of these forces. Because of these forces, what are we going to get? We're going to get I naught theta double dot plus. See, if it is rotating in the forward direction, the inertia force is going to be applied in the opposite direction. Okay. Other than that, the two forces will also produce the moment in the that direction only. So I theta double dot plus k1 r square theta because kr theta force into r and plus k2 r theta minus x into r is equal to 0. So we have found the second equation as well. This is the second equation. See, we have a forcing function, so definitely our oscillations are going to happen at that frequency itself. So we can assume the solution as x as capital X cos of omega t plus phi and theta is equal to capital theta cos of omega t plus phi. For now, I don't know what is going to be the condition for the amplitude of oscillation of x going to be 0. What I'm doing is I'm finding out the solution. I'm just finding out the solution because once I get the solution, what I can do is I can use that solution, the amplitude equation, in order to find out the condition when the amplitude of x is going to be 0. So when I'll put these two, putting in the main equations, what do I get? The first equation I get is minus of m omega square plus k1 plus k2 plus I c omega into x minus k2 r theta is equal to f naught. Second equation minus of k2 r x plus minus of I naught omega square plus r square k1 plus k2 theta is going to be equal to 0. We have done nothing. We have taken the solution in terms of cos. We have differentiated it to get x double dot and theta double dot, put it in the equation, and then did nothing but equated the left hand side and the right hand side values of coefficients of cos functions. Only cos is going to come, sine is going to come, and then we have a iota with it. Okay, so this is what it is. So using this equation, if we'll find out the solution, okay, we just have to apply some algebraic manipulations and everything, which I'm not getting into because there is not much time that is remaining in the class. So doing all the algebraic manipulations and everything, we are going to get the equation of x and theta. Okay, and once we get the equations of x and theta, we can actually use it in order to find out the condition for which this is 0, right? Because we assume the solution of x as this, sorry, and that is we have to make x is equal to 0. We cannot make cos omega t plus phi as 0. So the best way is we make x is equal to 0. If capital X is equal to 0, then small x is also going to be equal to 0. Just a second. Okay. So after doing all the mathematical manipulations and everything, I'll just write the final equation. So for capital X and theta, anyways, we are concerned about capital X, but I'll write the equations for both. So for theta, the equation will turn out to be minus k2 r f naught whole divided by k2 r whole square minus m omega square plus k1 plus k2 plus iota omega c into minus I naught omega square plus r square k1 plus k2. So this is the equation for the value of capital theta, which is the amplitude of oscillation of the disk. This is basically the amplitude oscillation of the disk capital M. And then we find out capital X, which is nothing but I naught omega square with a minus plus r square k1 square not square k1 plus k2 into f naught divided by minus of m omega square plus k1 plus k2 omega c into I naught omega square plus r square k1 plus k2 minus k2 r square. So these are the, I'll write also amplitude of oscillation of the mass small m. Okay, so these are the two equations that we got. Now, if you look over here, we are not concerned about the complex terms that we are getting over here. See, because we have a dashboard involved in the system, the complex term is definitely going to come, right? That complex term is definitely going to come. We cannot avoid it. But over here, we don't have to find out the full solution. What we need to find out is just the condition under which the steady state displacement of mass m will be zero. We need to just find out the condition. So looking at this equation, we don't have to get worried about how to deal with complex equations and everything. We just have to find out the condition. Now, if you see over here for the capital X term, we have a numerator which is a sum of two terms. If I make the numerator equal to 0, I'm going to get the condition when capital X is going to be equal to 0, right? Correct? That is what the case is. Okay. So for the numerator, we have minus of omega square plus r square k1 plus k2 f naught is equal to 0. F naught cannot be equal to 0 because if f naught is equal to 0, then there is no uh, input to the system. It becomes a system which is going to have any kind of a movement only if we give it a some initial perturbation. Otherwise, it is going to be there with the static case. Okay, so f naught cannot be equal to 0. That is not we are concerned about. So r square k1 plus k2 is going to be equal to I naught omega square. So this gives I naught was taken as I plus mr square. Okay, so I was not actually given in the system, but we consider this. If we take it as 0, we have r square k1 plus k2 plus, not plus, is equal to mr square omega square. So the best way of, you know, see, because omega could be anything. Omega could be anything. We cannot constrain omega if we are designing it in such a way such that we want small x movement to be 0. We cannot, like, if we design everything and then we put the values and then we find out that okay, the system is going to damp out, like the value of x is going to be 0 only for a certain value of omega. But as an engineer, we never work like that. We work in the other way around. We If my system is concerned about having any kind of frequency, omega could be any value, right? So what I'm going to do is I'm going to find out that what are the operating conditions under which my system is going to work. If I know the operating condition, I know the values of omega, right? I know the values of omega, or I know the single value of omega. For that value of omega, if I want my system to be designed in such a way such that x1, not x1, here we have only x, such that x to be equal to 0, what I can do is I can choose the spring stiffness k1 and k2. Because when you look into the disk, it is difficult for us because we will need to manufacture the disk again and again, right? But if we choose the stiffnesses k1 and k2, that I can change the stiffness k1 and k2. So for every value of omega, I can change the value of k1 and k2 such that this condition is always satisfied. So this is the condition so that the steady state displacement of m, which is x, is 0. I hope you understand that what is the need of writing steady state solution, right? Here it is mentioned steady state displacement because when we are talking about a system which has a dashboard involved, what is going to happen? See, our system is going to have a vibration because of two things. Okay, the first one is going to be because of forcing, and the second one is going to be because of the natural frequencies of the system. The natural frequency of the system is going to get involved in the into the response of the system because of the perturbation. Because of the perturbation. Okay, so initially when I give some kind of a perturbation to my system, what is going to happen? Or even if I give the forcing, my system is going to have three components. First one because of the first natural frequency, second one because of the second natural frequency, because we have 2 degree of freedom system, and the third one which is going to be the particular integral, which is because of the f naught sine omega t. But since we have a dashpot involved in the system, the dashpot is going to take away the energy which is because of the natural frequency. Okay, the free energy. It is going to take that. Okay, because of the natural frequency, we have the free vibrations. So that free vibration, the dashboard is going to take away with time. Depending upon whether my system is underdamped, overdamped, or critically damped, the time will depend on that. Anyways, it is going to take up the energy which is causing the natural frequency oscillation. Okay, so once it will take up that energy, then only the vibration which is present over there because of the forcing frequency is going to take place, which is what we call as the steady state displacement. Steady state displacement is mostly concerned about the system response because of forcing. So the component of the solution, that is why over here, if you look here, when we assumed the solution, we assumed it in terms of omega t, not in terms of omega n1 or omega n2, in terms of omega t, because we are considering the steady state solution. These were the steady state solution. We assumed it. Okay. So yeah, and then we got the condition. Okay. So this was it for today's live session. I hope that these questions will be helpful for you to solve the assignment problems. And I hope you people are enjoying the course. So if you have any doubt, you can ask, or maybe now you don't have any doubt, then you can ask in the next live session. Otherwise, for now, we'll just end the live session. Okay, I think there is no doubt. So we'll end the session. If you have any doubt that will come to you in the next week, then please ask, as only 4 weeks of the live session are remaining. And after that, I am going to take an extra session for you people in order to, answer if you have any queries regarding any of the course. So, okay, that's it. Thank you for attending the session, and we'll meet next week, Tuesday, 6 p.m.